In this video, I'd like to talk about Dalton's law of partial pressures. This is one of the gas laws that you may remember from the first year of chemistry, but in AP we're going to go into this in a little bit more detail. So let's begin. Dalton's law of partial pressures says the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of each gas in the mixture. Well, what do we mean by partial pressure of a gas in the mixture? The partial pressure of a gas is defined as the pressure that that gas would exert if it were alone by itself in the container. And Dalton's law basically says, in written form, that the total pressure is equal to, as you see here, the sum of the partial pressure of gas A plus partial pressure of gas B plus all the way up to the partial pressure of the nth gas. So, what does this look like? Well, let's say that I have gas A in a given container of a certain volume, and it exerts a pressure of 1 atmosphere. I take out gas A, and then I fill it with gas B in the same volume container at the same temperature, and it exerts a pressure of 2 atmospheres. Well, suppose I combine those two samples of gas A and B together in the same container, same volume, same temperature. What pressure would they exert? Yes, you guessed it, exactly 3 atmospheres of total pressure. So, let's see what type of problems we'll encounter with this law. So, first let's derive an important equation. Here is Dalton's law of partial pressures. The total pressure, as we said before, is equal to the sum of the partial pressures in the mixture. Well, we know that the ideal gas law says that pressure times volume equals moles times R times temperature, or rearranging, pressure equals nRT over V. Well, I can simply write out Dalton's law of partial pressures, replacing each term with a term that is corresponding to that particular gas. So I can say that the total pressure is equal to the moles of gas A times RT over V plus the moles of gas B times RT over V plus ... plus up to the moles of gas N times RT over V. So if I were to factor out RT over V, I see that the total pressure equals Na plus Nb plus ... up to moles of N times RT over V, or more succinctly, the total pressure is equal to the total moles times RT over V. And that's a pretty important conclusion. What that tells us is that in a mixture of gases, the total pressure exerted depends only on the total number of moles of particles, not on their particular identities, such as the molar mass. And that kind of makes sense. If we think back to the kinetic molecular theory of gases, we'll recall that the pressure exerted by a sample of gas arises from the collisions, the elastic collisions of those particles against the inside of the container. They exert a certain force. The total force exerted by those collisions, which is directly proportional to the number of particles, is what results in the pressure. So it seems to make sense that the pressure will depend on the total number of collisions, and therefore the total number of particles, and not on what those particular particles are. So here's an example of a problem that we can solve. A mixture of gases contains 5 grams each of nitrogen and fluorine in a 1 liter container at a temperature of 298 Kelvin. Calculate the partial pressure of each gas and the total pressure exerted by the mixture. Well, we know that in order to calculate the partial pressure of each gas, we will need to know the moles of each gas, so let's begin by converting the masses of nitrogen and fluorine into moles. So my moles of nitrogen will be equal to the mass divided by the molar mass. Remember, nitrogen is diatomic. That gives me 0.178 moles of nitrogen. And the moles of fluorine will be equal to the mass of fluorine divided by the molar mass of fluorine. Again, remember, fluorine is diatomic, is a pure element, and that gives me 0.132 moles of fluorine. Now, I can easily calculate the partial pressure of each gas because I know the moles of each gas in the mixture, the temperature and the volume, so I can simply convert these moles into pressure. The partial pressure of nitrogen is moles of nitrogen times RT over V, or 0.178 moles times the gas constant. Notice I'm plugging in both the number and the unit, as you're required to do, no matter how tedious you might find it. and that gives me a partial pressure of 4.35 atmospheres of nitrogen. I can do the same thing for fluorine. The partial pressure of fluorine will be the moles of fluorine I calculated times RT over V, 0.132 moles, times the gas constant, times the temperature, all divided by the volume, to give me 3.23 atmospheres of fluorine. Notice that it doesn't really matter that this happens to be a mixture. It would be the same if each of these gases was by itself. So now I can simply say the total pressure will be equal to the sum of the partial pressure of nitrogen gas plus the partial pressure of fluorine gas. I can simply plug in what I calculated, 4.35 atmospheres of nitrogen plus 3.23 atmospheres of fluorine, or my total pressure equals 7.58 atmospheres, which is equal to 4.35 atmospheres plus 3.23 atmospheres. Now, thinking back at the equations we just looked at, you may realize that there is another way we could solve this problem. Check this out. We could also say that the total pressure, which is what the question was asking for in the first place, is equal to the total moles times RT over V. Well, we calculated how many moles of each component we had. Let's simply add them together. So in place of total moles, I will put in 0.178 moles of nitrogen plus 0.132 moles of fluorine times R times the temperature, all divided by the volume of the container. Remember, temperature and volume remaining constant. And I get, what do you know, 7.58 atmospheres, which is exactly the same result. Do it either way, whichever one is less work for you. In the next video, we will talk more about how the partial pressure of a gas is related to the mole fraction of the gas in a mixture. See you then.